Today, we're going to pull back the curtain on a hidden logic that powers just about everything you do online. We're talking finding the fastest route with your GPS, seeing updates from friends on social media. It's this one big idea that turns total chaos into perfect order. I mean, really think about it for a second. You punch in a destination, and instantly your phone figures out the absolute best route, even dodging traffic you had no idea was there. It feels like pure magic, right? Well, it's not. It's just a really, really clever way of looking at the world. And there it is. That's the secret. Your map app, your social media feed, the entire internet. They don't see a random jumble of places and people. They see a beautifully interconnected puzzle, a structure called a graph. Okay, so here's our game plan. We're going to break down what a graph actually is, then we'll look at a few different types. After that, we'll see how a computer even navigates them, and we'll uncover that algorithm that finds the shortest path. And finally, we'll see why this stuff matters in, well, pretty much every part of our lives. All right, first things first. What in the world are we even talking about when we say graph? Let's get right into the basic building blocks. So at its very core, a graph is ridiculously simple. It's just a bunch of dots and lines. That's it. Now, in the fancy computer science world, the dots are called vertices, or nodes, and the lines connecting them are called edges. But really, all it is a set of points and a way of showing the relationships between them. You know, the easiest way to picture this is with a regular old map. Every city is a vertex, a single dot, and every road that connects two cities, that's an edge. And just like that, the entire complicated highway system becomes a simple, organized graph. So you might be thinking, hey, this kind of sounds like a family tree, and you're on the right track. But that's a key difference. A tree is a very specific kind of graph. It's got a strict hierarchy, one root at the top, and absolutely no loops. But let's be real, most real-world networks are messy. They have cycles, you could have all sorts of paths between 2 points, and that's what makes graphs so incredibly powerful for modeling how things actually work.
Now that we've got that basic idea down, let's build on it, because not all connections are created equal, which means we actually need different kinds of graphs to solve different kinds of problems.
The simplest type you'll run into is an undirected graph. Think of this like a friendship on Facebook. If you're friends with someone, they're friends with you, right? The connection is a two-way street. The relationship just exists between you two, no direction needed. But then you've got something like Twitter or Instagram. You can follow someone, but they don't have to follow you back. That's a directed graph. The edges are all one-way streets. The relationship has a very specific direction. It goes from A to B, but not necessarily B back to A. And this brings us right back to our map app. A weighted graph adds this whole other layer of critical information. Each edge, or in our case, each road, has a value attached to it, a weight. Now, this could be the distance in miles, or the time it takes to travel, or maybe even the toll cost. This is the crucial bit, because this weight is what lets us find the best path, not just any old path. Okay, so we've got these networks. But if you're a computer, how do you actually go through one in an organized way? How do you make sure you visit every single spot without just getting lost and going in circles forever? Well, there are two main strategies for this. So you can see the two main approaches here. Depth first is kind of like diving headfirst into a maze. You just pick a path and go as deep as you possibly can until you hit a dead end. Then you backtrack and try another one. Breadth first, on the other hand, is way more methodical. It's like exploring a city one neighborhood at a time. You check all your immediate neighbors first, then you check all of their neighbors, expanding outward in these nice, neat circles. And that, my friends, brings us full circle. We've got our weighted graph, we have a way to explore it, so now we can finally answer that question from the beginning. How do we find that fastest route? Finding the most efficient route in a really complex, weighted graph, that requires a very special tool. And in this case, it happens to be one of the most famous and elegant algorithms in all of computer science. It's called Dijkstra's algorithm. It's named after the computer scientist who came up with it way back in 1956. And the pure genius of it is that it doesn't just find one path. It systematically and super efficiently finds the shortest path from where you start to every other single point in the network. The logic behind it is surprisingly simple and elegant. First, you just set things up. You're at the starting line, so your distance is 0, and every other place is basically infinitely far away. Next, you update and pick. You look at all your immediate neighbors, figure out the distance to them, and then you jump to the closest one you haven't been to yet. And finally, you just do that again and again and again. You just repeat that second step, always checking neighbors and moving to the closest one until you've mapped out the shortest path to everywhere. Now, Dijkstra's is definitely the star of the show for things like roadmaps, but it does have its limits. For more complex problems, like, say, in financial networks where you might have negative costs, there's another algorithm called Bellman-Ford that can handle those really tricky situations.
So why does any of this matter? Because here's the thing. Once you start thinking in graphs, you start realizing that these networks are absolutely everywhere. This isn't just about maps, not even close.
I mean, your social network? That's a graph of people and their connections. The entire internet. It's just a gigantic graph of websites all connected by hyperlinks. If you're managing a big project, a dependency graph shows you which tasks have to get done before others can even start. Even AI uses graphs to figure out how ideas and words relate to each other. They are the fundamental blueprint of connection.
So here's the real takeaway. Graphs aren't just some abstract data structure. They are a language for understanding connections. This hidden logic is structuring our entire world in countless ways we never even see. So the only question left is, now that you can see the network too, what problems are you going to solve with it?